This lesson is an overview of the topic uniform circular motion. You have probably seen questions such as this. The wheel of a grinder makes 100 pi radians per second. What is its angular speed in revolutions per minute? But before I answer such questions, I'd like to go through certain important concepts in uniform circular motion that we need in order to understand such questions. Now, how am I going to cover these concepts? I have decided to write down a few questions that can serve as a guide to how to understand the various concepts in uniform circular motion. For example, the first question: an object moving with the constant speed in a circular path is said to accelerate. We want to explain how such a situation comes about. In question number 2, we want to describe centripetal acceleration and centripetal force, because these are new concepts. Question number 3, we want to describe what provides centripetal force for various situations in everyday life. Question number 4, we want to state and explain factors affecting centripetal force. And in question number 5, we want to derive the equation for centripetal acceleration. So all these are concepts which are important in this topic, uniform circular motion. So let's go straight to the first question. An object moving with constant speed in a circular path is said to accelerate. Explain. You have just seen that this small object here moving in this circular path and its speed is constant. First of all, the meaning of uniform circular motion is this. We have an object which is moving in a circular path with a constant speed. That kind of motion is referred to as uniform circular motion. So simply put, uniform circular motion means an object moving in a circular path with uniform speed or constant speed. So that is the meaning of uniform circular motion. Now, such an object is said to be accelerating. Can we be able to explain how this comes about? Let's look at a situation whereby we start with this object. This small object here may be a stone tied to a piece of thread, and then that thread is whirled around in a circle. This circle may be a vertical circle or horizontal circle. Now let's assume that it starts from this point A here, and then it is moving like that. You realize that the length of this string becomes the radius of the circular path. So this is radius and this is radius. So this radius is going to sweep a certain angle here at the center, which we are going to call theta. And then the path followed, or the distance covered by this particle in moving from point A to point B, this length of the arc here, from this point all the way to this point, we are going to give it the symbol S. The arc length is S, while this is the radius. I'll come to this point later on. But at this point, I want to imagine, since it is starting at point A, let's assume that its speed is 20 meters per second. 20 meters per second. And because it's uniform speed, its speed at point B is also 20 meters per second. Even when it goes to some point here, its speed will still be 20 meters per second. So its speed is constant. That is, the speed is uniform. How about the velocity? The main difference between speed and velocity is this. While speed is a scalar quantity, velocity is a vector. A vector quantity has two aspects. It's got magnitude and it's got direction. Notice that when I'm describing the speed of this object, I'm just concerned with this number here, 20 meters per second throughout. I'm not concerned with the direction in which it is moving. So I am describing speed. because speed is a scalar quantity and it has got magnitude only. Magnitude is just a number and a unit. The moment I say that it is 20 meters per second in the direction of this arrow, the moment I bring in direction, I will no longer be talking about speed. I'll be talking about the velocity, because I have mentioned two things, the magnitude and the direction. So at point A, this is the direction of travel and the magnitude is 20 meters per second. When it is at point B, this is the direction of travel and the magnitude is 20 meters per second. You will agree with me that these two directions are different. So due to the fact that the direction of travel has changed, the velocity of this object has changed. So although this object has got uniform speed, its velocity is continuously changing because of change in direction of travel. So the velocity is changing. Now once we agree that the velocity is changing, we go back to the definition of acceleration. Acceleration is change in velocity divided by the time it took for that velocity to change. So any object which experiences a change in velocity must be accelerating. So those are the 3 points which you need to mention, that although the speed is constant, the velocity is changing because the direction of travel is changing, and any change in velocity is an acceleration. And you see, we have answered this question here. We have an object moving with a constant speed in a circular path, and it is said to accelerate. Can we be able to explain how it is said to accelerate? Of course we can. We need to start by saying that the speed is constant, alright, but due to the fact that direction of travel is changing, the velocity of that object is changing. The moment we mention the velocity changing, we are just one step away from stating that the object is accelerating, because any change in velocity is an acceleration. So that is how we would answer this first question. Now let's look at the second question. In the second question, we want to describe centripetal acceleration and of course centripetal force. Again, these are new terms. Now remember, this is just an overview, so I'm going through the main points. We have just seen that this object is accelerating. Can we be able to state the direction of that acceleration? Let's assume this 20 meters per second here is u, and this 20 meters per second here is v. So we've got u, the initial velocity, and v, the final velocity. This one is a small angle that we are going to call theta. Now, in order for us to get change in velocity, we need to get the final velocity minus the initial velocity. The change in a physical quantity is always equal to the final of that quantity minus the initial of that quantity. Remember, velocity is a vector. So let me create some more space here because I need to use graphics in order to show this. So we've got v minus u. I want to write this expression like this: v plus minus u. Now this one does not change the expression. Think about two numbers, the difference between two numbers, 7 minus 5. This one could be written like 7 plus minus 5. This is just simple algebra, and we know that I have not changed this equation at all. 7 minus 5 is the same as 7 plus minus 5. So I want to write v minus u as v plus minus u. Let's see what happens when I use arrows. Where is my v? My v is here. Now remember, the length of this arrow represents the magnitude of the velocity, which is 20 meters per second. That is why the length of this arrow is equal to the length of this arrow. Plus, now when we are dealing with vectors, if you're given that there is a certain vector which is pointing in this direction and you call it vector A. If you have given a similar vector of the same magnitude but pointing in the opposite direction, we will say that it is minus A. I want us to use this analogy here. So, if U is like this, minus U will be like this. So, we are adding minus U, and minus U is definitely like this. And remember, these two arrows have got the same magnitude. Now, something else. This angle here is theta. So, definitely this arrow here has been turned from the vertical through an angle equal to theta. So, this angle here is theta. Now, this is addition of vectors. Remember, this is V, this is minus U. I want to add these two vectors, this addition here, this addition here. So in order to add vectors, we always connect them head to tail. So I'm going to get a V because it was the first vector, and then I bring in minus U, which is like this. And then this theta obviously comes here. This is theta. So this is a V, this is minus U, and when we add vectors, when we connect them head to tail, the resultant vector is given by this arrow here, from the first tail to the last head. After connecting the two vectors head to tail, then the resultant is given by drawing a line from the first tail to the last head. This is the change in velocity. When this angle, if theta is made to be very, very small, this delta V, change in velocity, is found to point towards the center of the circular path. This is delta V, pointing towards the center of the circular path. I'm driving at the point here that for me to talk about acceleration and to know its direction, I must know something about the change in velocity. Because I'm just one step away from stating that the acceleration is just dividing what I have here by the time it took for this velocity to change. So that is why I'm struggling with this change in velocity. The point I want to make here is the change in velocity is towards the center of the circular path. And that implies that the acceleration is also in the same direction. So I've gone through all this trouble to show that the change in velocity is towards the center of the circular path. Hence, it follows that the acceleration is also towards the center of the circular path. This acceleration that the object has when the object is moving in this circular path is referred to as centripetal acceleration because it is always pointing towards the center of the circular path. It is always searching the center of the circular path, and that is why it is called centripetal. Centripetal means center seeking. Center seeking. So let's sum up this part by saying the following. When an object is moving in a circular path with constant speed, it is accelerating because the direction of travel is changing. And when the direction of travel changes, then the velocity is changing. And any change in velocity is an acceleration. The direction of the change in velocity is towards the center of the circular path. If that change in velocity is divided by the time it took for the velocity to change, we get the acceleration, which is also towards the center of the circular path. Now, since this acceleration is always pointing towards the center of the circular path, it's called centripetal acceleration. And then from there, we want to talk about centripetal force. How do we bring in force? We know from Newton's second law of motion that any object which is accelerating must be experiencing a resultant force. And the direction of that force is the same as the direction of the acceleration which it produces. So in this equation represents Newton's second law of motion, where this is the resultant force which is acting on an object of mass m, and when it acts on that object, it produces an acceleration a on that object. The direction of this acceleration is the same as the direction of this force, because it is this force which is producing the acceleration. So why don't we reverse this argument and say, if we know the direction of the acceleration, then we know the direction of the force which was producing it in the first place. We have just proved that an object which is moving in a circular path with a constant speed is accelerating towards the center of the circular path. So, due to the fact that it is accelerating, there must be a resultant force which is producing that acceleration. That resultant force is referred to as centripetal force. Centripetal force. And it is in the same direction as the centripetal acceleration. So, three things which are pointing towards the center of the circular path. One, there is change in velocity, which is directed towards the center of the circular path. The acceleration is also directed towards the center of the circular path. And the centripetal acceleration, the centripetal force which is producing this acceleration is also directed towards the center of the circular path. To conclude this question, we can say that every object which moves in a circular path must be having an external force which is being exerted on that object, which is making the object to move in a circular path. In other words, when you see an object moving in a circular path, such as electrons orbiting the nucleus of an atom, you should know that there is a centripetal force which is acting on that electron. Think about a planet which is orbiting the sun. There must be a centripetal force which is acting on that planet, making it move in a circular path. Think about satellites. Think about other simple objects, even a car going round a circular bend. There must be a centripetal force which is acting on it, making it to move in a circular path. In the next question, of course, we are going to look at what provides this centripetal force. And let's quickly look at that question. So over here in this question, I want to describe what provides centripetal force for various situations in our lives. I've just mentioned that the electron orbiting the nucleus of the atom, that the electrostatic pull on the electron by the nucleus of the atom, because the nucleus is positively charged and the electron is negatively charged, and the electron is orbiting the nucleus, then the force which makes it move in that circular path, or the force which provides the centripetal force on the electron, is the electrostatic pull on it by the nucleus, by the positively charged nucleus. I want you to observe two terms I'm using here. I'm talking about what provides the centripetal force on what object, and it is provided by what. For example, let's talk about planets orbiting the sun. If this is the sun and maybe we've got a planet here, maybe the Earth, then the gravitational pull on the Earth by the sun, I want you to observe those words very carefully. Gravitational pull exerted on the Earth by the sun provides the required centripetal force on it to make it orbit the sun. So over here it is the electrostatic pull. Here it is the gravitational pull on the Earth by the Sun. How about satellites orbiting the Earth? Again, it is the gravitational pull on the satellites by the Earth, which provide the necessary gravitational pull on the satellite. Car going round a bend. This one, the centripetal force on the car is provided by the sideways frictional force on the tires by the road. Frictional force on the tires by the road, which provide the necessary centripetal force. A cyclist negotiating a corner, the same thing, the sideways frictional force. How about a stone tied to a string and whirled around a circular path? Or this one should be path here. The tension in the string provides the centripetal force on the stone. How about a plane looping the loop? A plane looping the loop. We'll be looking at this example, and we'll be looking at what provides the centripetal force on the pilot who is on a seat. And there are two forces we'll be concerned with: the weight and the reaction force. The resultant of those two provides the centripetal force on the pilot. A car going over a Hamburg bridge. What's a Hamburg bridge? Along highways, you've seen this kind of bumps. They're usually very long, and usually cars don't slow down when they are going over these kind of bumps. What provides the centripetal force on this car? Again, we'll be studying these special situations, and we'll again see it is the resultant force between the normal component of the contact force and the weight of the car. There are so many situations where you have objects moving in circular path, and we need to know what provides the centripetal force for those in those situations. Now let's look at question 4. Now, in question 4, we want to state and explain factors affecting centripetal force. We'll be able to understand this after we derive the equation for centripetal acceleration, because that centripetal acceleration, which is given by v squared over r, gives us two factors, and then of course the third factor is the mass. Of course, here we can just state them that the first factor is the mass of the object. The heavier the object, the more centripetal force you will need. How about the speed of the object? The higher the speed, the more the centripetal force you're going to require. And of course, the smaller the radius, the higher the centripetal force. Again, we are going to study each one of these and see how it comes about. So simply put, the factors which affect centripetal force are 3 of them: the mass of the object, the speed with which it is moving along the circular path, and the radius of the circular path. We say that the centripetal force is directly proportional to the mass. Centripetal force is directly proportional to the square of the speed, and the same centripetal force is inversely proportional to the radius of the circular path. Again, we'll talk about that. Let's quickly go to question 5. Now, in question 5, we say this is where the rubber meets the road, because we want to derive the equation for centripetal acceleration. Let's consider the same object which is moving in a circular path. There's a circular path, and this was the starting point of the object. We call it point A, and this is point B. This is the radius of the circular path. Again, this is the radius. So since it is moving from point A to point B, the length of the arc AB is S. The radius sweeps an angle theta, like that. Of course, this is the radius. At this point, we want to define the angle theta. Angle is a physical quantity, and it is defined as the ratio of the arc length to the radius of the circular path. So theta is equals to S over r. This is the equation which is associated with the definition of angle. Now, this may come as a surprise to many students. They have never thought about defining angle, but just like you define physical quantities such as pressure, density, and so forth, you are supposed to define angle. When you define pressure and you say pressure is defined as force exerted normally on unit area and that pressure is equals to force over area, the same thing happens to angle. Angle is defined as the ratio of the arc length to the radius of that arc, and the equation which is associated with that definition is angle is equals to arc length divided by radius. Now, the units of pressure is newtons per meter squared or pascals. The same thing happens here. The unit of angle is radians. Radians. I know you have measured angles in degrees. It's high time you learned that the SI unit of angle is radian, abbreviated as RAD. In mathematics, sometimes we use the letter C. The letter C. Let us say maybe you say angle is going to be equal to pi radians. You write a power C there to mean the same thing. But in physics, I'm going to use RAD, radian, to represent the SI unit of angle. Now, since this one is a new unit, I want to define 1 radian. 1 radian is defined as the angle subtended at the center of the circle by an arc whose length is equal to the radius. For example, if the radius of the circular path is 1 centimeter, this one here, 1 centimeter. If this object moves through an arc whose length is also 1 centimeter, there isn't much space there, but this is 1 centimeter, then this theta is equal to 1 radian. So simply put, the radian or 1 radian is the angle subtended at the center of the circular path by an arc whose length is equal to the radius of that arc. Now, having stated that, I want to go back to this situation and say that at this point we can multiply both sides by r, and we are going to get S is equal to r theta. And remember, our aim here is to derive an equation for centripetal acceleration. We know that centripetal acceleration is given by v squared over r, something like that. Now, over here, I've got the final velocity, which is tangential to the circle at that point, which is v at B. Its magnitude is just v. Also at A, I've got the same speed, v. And I've just seen that if I want to get delta v, I just need to get that v, which was at an angle like that. There is another v here. This was the final velocity v. This one was the initial velocity minus v. And the delta v is here. Delta v. We have just seen this. It's only that I'm using the same symbol v to represent final velocity and initial velocity. But just understand that I want to express a point here. We have just seen that if this angle is theta, then this angle must also be theta. Now, we can also be able to define this angle theta, especially if it is very small. Let us call it delta theta, very small, because we have seen when it is very small, that is when delta v is directed towards the center of the circular path. So this delta v can be defined as the arc length, which is delta V, divided by the radius of the circular path, which happens to be V. So, over here, we have also seen that if we want to get theta, we do S over R. We can say delta theta, I'm just using this equation here, is going to be equal to a small change in length, delta S over R. Bear these two equations in mind. Delta theta can be defined as delta V over V, and delta theta can also be defined this way. So, since delta theta is equal to this and delta theta is equal to this, I can say this one is also equal to delta V over V. And of course, over here, I can make delta V to be the subject by multiplying both sides by V. So I'm going to have delta V is going to be equal to V delta S over R. Okay, things I'm getting a bit crowded here, but I hope you can be able to follow. Delta V is equals to V delta S over R. Now, at this point, I want us to think about speed. Speed, V, is equal to distance covered divided by time taken to cover that distance. So, if we think about this object having traveled a small distance, delta S, along the circumference of the circular path, then we can say that that speed is going to be equal to delta S over T. So over here we can say that this implies that, suppose I want to make delta S to be the subject, it's going to be equal to V times T over here. So I'm going to have delta V is equal to V. Instead of delta S, I'm going to have V. This one is V. Delta S is V times T. So I've got a V times another V divided by R. Let me write it carefully here. Delta V is going to be equal to V times another V times T over R, and this one will be equal to V squared over R times T. We're just one step away from deriving this equation here. So I'm going to divide both sides by T. If I divide this side by T, I divide this side by T and this side by T, you will definitely be able to see that I've got delta V over T. And delta V over T is acceleration. And over here, I've got V squared over R. V squared over R. And that is how we would arrive at the equation for calculating centripetal acceleration. Centripetal acceleration. So it starts from the definition of angle, where I went to the definition of angle as the ratio of the arc length to the radius of the circular path. Then I defined the unit of measurement of angle, which is radian. Then from there, I went to how I obtained delta V by putting these triangles together. And then I can be able to see that this can be some kind of an arc. And this is the radius of that arc, because this is V and this is V. This length and this length, it is the same. Just like this is R and this is R, and this one is delta S. So similarly, if this one is V and this one is V, this one is delta V. So we can be able to define theta from this equation here. And let's not forget that the same delta theta is defined here. So delta theta is equals to this, and delta theta is equals to this. This gave me now the permission to equate this equation to this equation. And once I did that, I got delta V to be equal to this. And then I brought in a simple definition. We remember the definition of speed as change in distance covered per unit time. And then we wanted it to write that change in length, the arc length, as the subject, because I wanted to substitute it here. And that is exactly what I did. And finally, this is what I get. So that is how we would derive the equation for centripetal acceleration. Now, these are just basics in uniform circular motion, and this is part 1. In part 2, I'm now going to look at applications of uniform circular motion, and I'll use questions as well as studying particular situations.